Let me start the recording. Yeah, Sheng, it's all yours.
All right. Good morning, everyone. I'm really excited to have all of you here. I wish this could be an in-person event, but I'll try my best to make this a good experience for Saturday morning. If you have any questions, you can interrupt. All right.
Shall I go ahead and
start?
I don't want you to stop if you're enjoying it.
It's worth here trying to figure out what they're talking. That's neat. That's an interesting.
I did, but I'm going to go ahead.
Okay. So let's start with a story. So about 100 years ago, there were 3 young physicists. They were sitting on a train and discussing the exciting new discoveries in physics. And one of them proposed that, you know what, we need a new mathematics where A times B does not equal to B times A. So we all learned in primary school that 3 times 4 is 4 times 3 is 12. But he's proposing that we need a new mathematics where A times B is not B times A. All right. Well, another guy said, you know what? This type of mathematics already exists. Really? No kidding. It even has a name. It's called linear algebra. Okay, nowadays, linear algebra is not something exotic. It's really one of the basic courses all the physics students have to take. But back to 100 years ago, very few physicists were familiar with linear algebra. So in linear algebra, you not only have numbers, you have vectors, you have metrics, and indeed, the multiplication of metrics really depends on the order. So A times B does not have to be B times A. All right. So shortly after this discussion, they indeed established a new formalism of physics, and that is called quantum mechanics. And turns out the difference between these 2 products is related with Planck constant, which is a characteristic number for the quantum world. I'm not sure if this story is true, but it likely is made up. But it's a good example to illustrate how the mathematics can bring in significant contribution to the development of physics. Actually, if we review the entire history of physics, you can see that every time when physics were looking for a new mathematics, something dramatic can happen. For example, when Newton were developing his theory of general relativity, of the gravity, he had to create his own mathematics, that is a calculus. And another example is Einstein. When he developed the theory of general relativity, he actually got stuck for quite a while. He was looking for a mathematics to describe it until his friend told him that, well, the tools that you need is within this Riemannian geometry. Okay. So by mid of last century, there were only 2 branches of mathematics that did not have real life application. One is a number theory, and the other one is topology. Right. Someone says there are 2 kinds of mathematics. The first kind of mathematics, you open a textbook, you read the first page, and you feel, okay, I do not want to continue. And the second type of mathematics, you open a textbook, you read the first sentence, and you feel you do want to continue. In my opinion, the number theory and topology really belongs to the second one. It's really something very hard to understand. Nevertheless, in the past few decades, this topology combined with quantum mechanics really brought in new gradients, opened new dimensions for our understanding of the matter. Right now, we're in a so-called topological revolution in the condensed matter physics. And the few pioneers of this field, won the Nobel Prize in 2006. So the core of this revolution is the following. In the past, we know that the difference between the phases really rely on the symmetry. I'm going to talk about this a little bit more later. But basically, we think if a matter changes from one phase to the other, there has to be a symmetry breaking. But now we know the symmetry breaking, this criteria of symmetry breaking is not complete. A lot of phases can be characterized based on the topology, not the symmetry breaking. Now, what is this topology? You probably all know this. If you take one piece of paper, you fold them, you stick it together, you can get a paper ring. But before you stick them together, if you twist it and then you stick together, you can get a so-called movie stripe. Now, between this paper ring and the movie stripe, there's a topology difference. The first one, there's no twist. The second one, there's a twist. Therefore, there's no way for you to change the first one to the second one without breaking it. This is a topological property. Topological property is a macroscopic property that does not depend on the details. For example, this movie stripe, you can bite, right? You can take off a piece of some corner. As long as you do not open it, it still has a one twist. That's a macroscopic property. There's a story. A young guy went to an old man with tremendous wisdom. And the young guy said, well, me and my wife, everything is very good, but there's always something wrong in the relation. So can you help me out? So the old man says, yes, I can, only if you bring me a piece of paper with only one side. Yeah, that's a movie stripe. So the old man meant to say, everything has two sides, right? But what he didn't know is this young guy actually is a topologist. So this young guy handed him a movie stripe. It only has one side. Okay, anyway, so this is one example. Another example you probably heard about is, a donut and a coffee cup has the same topology. It has one hole. So how many holes you have is a topological property, because it does not depend on the detail. If you have one apple, right, there's no hole, you have one bite, even though you disturb it a lot, there's still one hole. So how many holes you have is a topological property. Just from our intuition, we already know this, but almost 200 years ago, mathematicians, they actually demonstrated this. So this is what Gauss have. He demonstrated that. Here's the equation. On the left side, he did his integral over the so-called Gaussian curvature. The Gaussian curvature is a quantity to decide how much it curves. If it's one piece of paper, there's no Gaussian curvature. If it's a sphere, perfect sphere, the Gaussian curvature is the same all over the sphere. He demonstrated that for arbitrary shape, if you do this integral over the Gaussian curvature, you can get integer number, and this integer number is related with how many holes. So this equation tells you that even if you change the Gaussian curvature, it doesn't matter. As long as you do the integral, you always get how many holes you have. So mathematically, you can demonstrate our intuition that how many holes you have does not depend on details. So now you wonder, well, how can this get related with quantum mechanics? Right? And how can this help you to understand the so-called quantum materials? When I say I study quantum material, obviously I do not mean I study how many holes I have on the sample I study, right? how can this help you? All right. Okay, a key great ingredient for this is a so-called continuous deformation. So if two things have the same topology, have the same, for example, a coffee cup and a donut, they have same number of holes. So in principle, you can continuously deform one to the other without breaking it. This is a key to the topology. All right. Anyway, how can this help us to understand materials? The story went back to 1879. So 1879, there's another young guy, Edward Hall. He was an American physicist. He was a student in Johns Hopkins. And he was considering this simple problem. Let's say if you have a piece of copper, some metal, you can run a current through the metal. So here I drew the current on the edge, but really I mean the current is flowing along the piece of metal. Now, if you stick a voltage meter on both sides, and the voltage, you can detect a voltage drop, and this voltage divided by the current is a quantity that everyone is familiar with, that is a resistance. But something interesting can happen if you apply magnetic field. If you have current along this direction, the electron is supposed to move in the opposite direction, but along this edge, along this long direction. He was thinking, what if you apply magnetic field? Actually, back to that time, Maxwell, in his book of Electricity and Mechanism, Maxwell made a comment on exactly this problem. The conclusion Maxwell had is magnetic field will do nothing on this electron. Well, Hall was very confused. Well, obviously, if the electron is moving this direction and you have magnetic field perpendicular to the page, there will be a Lorentz force, and the electron is going to deviate from this direction. And at the end, you might have negative charge accumulated on one side and positive charge accumulated on the other side. So he did an experiment under the guidance of his advisor, and indeed, if he put a voltage meter across the sample, so perpendicular to the direction of the current, and he was able to detect a voltage drop. And in the same way, we can use voltage drop divided by current, we can define another resistance. And this is called Hall resistance. So indeed, he detected a voltage drop. And due to this voltage drop, he got a faculty position in Harvard. Well, he did not win Nobel Prize. Okay, so this is a Hall resistance. Now, turns out here I'm showing the Hall resistance as a function of magnetic field. So you can imagine the Hall resistance will go linearly up. If there's no field, there's no Hall resistance. If you have larger field, you have larger Hall resistance. At the bottom, I'm showing the normal resistance. So I put RXX to indicate the voltage drop and the current is along the same direction. This is a normal resistance. The normal resistance will not change much in the field. So this was what he discovered in 1879. 100 years later, well, 101 years later, another young guy was repeating this experiment. So this is Dr. von Klinsing in Germany. He was repeating this experiment. But of course, after 100 years, the technique was developed a lot. So people were able to go to much lower temperature and a much higher magnetic field. But more importantly, 100 years ago, when Hall did this experiment, he really used a chunk of metal, one piece of chunk. But after 100 years, now people were able to make so-called 2D electrons. So they were really able to confine electron in a two-dimensional shape. So he was studying the so-called 2D electron gas. At the bottom, you can see this is almost the same geometry. You have electron, your current moving from up to down, and then he put some leads across the sample to take the voltage drop. So the major difference is before that the three-dimensional system, now he's doing study in the two-dimensional layer. Well, this is what he discovered. You can see, okay, here the red curve is the Hall resistance. So I'm showing the Hall resistance as a functional magnetic field. In the very low field region, you can see indeed it increases linearly. But as you increase the magnetic field, it starts to deviate. You can see the state-like features. And what's more surprising is this state-like feature, the resistance, the Hall resistance, is exactly quantized in terms of h/e squared. So here I'm showing Hall resistance divided by h/e squared. You can see the final step is 1. So that means the resistance exactly h/e squared. And another step you can see is 0.5, so half of this value. Now, in the same time, if you can measure resistance, the green curve is the resistance you can see. Wow. When you have the step-like feature, the resistance, the green curve, really drops to 0. You have a perfect conductor. So what's going on? Now, as I said, he is studying a 2D electron gas. So electrons are confined in a 2D plane. In this scenario, if you apply magnetic field, we know the electrons will move in a circle. All right. If the magnetic field is very strong, what this means? This means the electrons will be confined to that point. The electrons can only move in a circle, but will never leave that position. So that simply means it's an insulator, because no one is gonna conduct the charge. But this cannot happen as age. As age, the electrons cannot complete the circle. In order to complete the circle, electrons has to get out of the sample, get into the vacuum, and comes back into the sample. That cannot happen. So what really happens as age is the electron will hit the wall and bounce back, and hit the wall and bounce back, hit the wall, bounce back. The net effect will be the electron will move in one direction. On the top, it's going to move to the right. At the bottom, it's going to move to the left. For a two-dimensional system, the age is one-dimensional. There's only, for a one-dimensional, there are only two possibilities to move, either right hand or left hand. On the top, there's only left moving electron. That simply means electron cannot be scattered. So the direction of the moving will not be altered, because there's no left moving channel. It can only move to the right. That means it's a perfect conducting age state. So in the bulk, it's an insulator. On the edge, it's conductor. It's a perfect conductor. So this obviously, that's what we saw here. And this obviously is very different from all the other insulator we know. For example, the silicon, right? Or the germanium that we use in the cell phone, in the computer. It's very different from those type of insulators. Silicon is insulator and the edge is insulating. Now, for this type of insulator, the bulk is insulating, the edge is a perfect conducting channel. Well, so we have a different type of insulator, but what really confuses people is, as I mentioned, in the past, people believe the different phases relies on the symmetry. For example, water, it can be a gas or liquid, and it can be a solid. The difference between the liquid and the solid is the symmetry. In the gas or liquid, the atom, is moving everywhere. It has all kinds of symmetries. You rotate or you translate, you still get the same gas. But for a solid, inside the solid, it forms a so-called lattice. The lattice can be a square, or it can be a hexagonal. If you look at one direction, if you look up or you look at diagonal axis, you look at a different thing. So for a solid, it loses certain symmetry. From a gas or from a liquid to a solid, there's a symmetry breaking. Now the same thing for magnetism. For iron, at very high temperature is paramagnetic, and the spin, which you can think of as the magnetic bar, points to all kinds of direction. In the low temperature, when it establishes a ferromagnetism, the magnetic moment points to a certain direction, and therefore you lose the time reversal symmetry. But turns out these two types of insulating state, a normal insulator state or quantum Hall insulating state, they do not break any symmetry. They have the same symmetry. So what's the difference between these two phases? Turns out it's a topology. Okay. Of course, when we say topology, we do not count how many holes we have on the quantum Hall state, but we can define a very
freezing up here.
similar way. Someone had a question. All right. Okay. So when it comes to how many holes we can really, use an integral. So we integrate the so-called Gaussian curvature to get how many holes we have. In quantum mechanics, we cannot do the Gaussian curvature, but we have a so-called Berry curvature. This Berry curvature tells you, you can think of that as the curve, the wave function. So we can do the integral over for this Berry curvature, and similarly, you can get some integer number, Chern number. Turns out that number is related with the quantized Hall effects. So you define a Berry curvature and you do the integral, and you can get some integer number. Turns out this integer number is related with the quantized Hall resistance, and therefore that is related with the age state. Okay, so as I mentioned, for topology, a very important thing is the continuous deformation. If two things have the same topology, you can continuously deform one to the other. Turns out, normal insulator and the quantum Hall, they have different topology. If you think of donuts and a ball, the normal insulator is a ball and quantum Hall is a donut. Therefore, they cannot be continuously deformed from one to the other. What does this mean? This means if you put the quantum Hall in a vacuum or just in the air, the vacuum is a normal insulator. On the edge, inside the quantum Hall is insulating. On the edge, it has to go from this quantum Hall to the vacuum because no continuous deformation can happen. That simply means as an edge, as a boundary, we have to break it. We have to break that energy gap for an insulating state. Therefore, you have this conducting channel on the surface. All right, so that's, it won the Nobel Prize. And it really started a new revolution. It tells us there's a whole class of material cannot be classified with symmetry, but only topology. Now, this is quantum Hall. That was 1980. in the past 40 years, starting with quantum Hall, this field expanded, and there are many, many new classes of topological materials. For example, if you consider electron spin, you can go from a quantum Hall to a so-called quantum spin Hall. And a quantum spin Hall is two-dimensional system, but you can expand from 2D system to a 3D system, a topological insulator. Another example, for a quantum Hall, we just apply the magnetic field. But if you can replace the magnetic field with internal magnetic moment, you can establish the so-called quantum anomalous Hall. And there are many examples. And really, turns out at least 1/4 of the material, 1/4 of materials that we know are topological non-trivial. Probably the number is still growing. So you may ask, so what, right? You can classify the material with a different category, but so what? This is very interesting from a fundamental level of physics, but also it's very interesting and very promising for the next generation of electronics. Now, we human beings already established a tremendous calculation power, right? We can do all kinds of complicated problems, but there are still some problems that are beyond our capability of calculation. Two examples is to factorize a large number. 6 = 2 times 3, that's a simple problem. But you can have a huge number, and it's going to be very hard to factorize. And indeed, our password depends on the fact that we cannot factorize it easily. Another example is to simulate large molecules. Right now, scientists are working hard to get the drug for the COVID, but it's only because we cannot simulate those large molecules. If we can, that can accelerate the speed to develop the new drugs. In order to solve this kind of problems, we need a so-called quantum computer. So a normal computer, we use a so-called bit. Bit is a two-level system that can be either 1 or 0. But in a quantum computer, we use a quantum bit. Right? There are all kinds of different quantum bits. You can do a superconducting loop. You can use trapped iron, or you can use, for example, quantum dots. But it's all some variation of quantum mechanic version of two-level system. For example, you have atom, you can have one energy level, you can have a next energy level. That's a two-level system. But for atom, it can not only be 0 or 1, it can also be in a superposition of two different energy levels. Therefore, we can build a quantum computer based on that. And over the past decades, there has been a great progress on this. Last year or two years ago, Google announced their quantum computer with 50 qubits. And they announced the quantum supremacy, which means quantum computer can beat the conventional computer in certain problems. So some of my friends ask me, well, my laptop is slow, I'm gonna replace it. Can I buy one of this quantum computer this year? Turns out we're still very far away from being useful for this real life problem. For real life problem, you need not only 50 qubits, you need 500 qubits. And majority of this qubits actually will not be for calculation, but it's going to be for error correction. The reason is the following. We not only need 500 qubits, we actually need 500 qubits to work in a coherent way. It's like running a company, right? A company is not a simple assembly of 100 people. A company is an assembly of 100 people working in an organized way and towards the same goal. The same thing for a quantum computer. We need 500 qubits to work in a coherent way. It turns out these qubits are very fragile. It can get disturbed easily and therefore lose the coherence. In order to solve that problem, one approach is to have millions of physical qubits, and majority of those is going to be for the decoherence errors. And this turns to be a very challenging problem. Yeah, question? Okay. Someone asked, what is a qubit? Okay, sorry. A quantum version of bit. A quantum version of two-level system. You can have light bulb, you turn it off, turn it on, that's a two-level system, right? It's two states. We can have a quantum version of two-level system. You can have atom, it has ground state, and it has a higher energy state, that's a two-level system. And but for a quantum version, you can either be in the ground state or a higher energy state or a superposition of these two states. Therefore, that is called a quantum qubit, quantum bit. Simply we say it's a qubit. All right. So this is one approach to do this. So have majority to fix the problem. But there's a different approach. Imagine we have a matter, we have a material. This material is made of ordinary atoms. But this material, if it has some non-trivial topology, some exotic properties, so this atom, this material actually can host a very exotic particle called anions, right? So anions so far is just some name for you, okay? Some anion, something called anions. Now, but keep in mind, these anions do not exist in the nature, right? And it's not something new. In the material, the anions actually are just electrons. But in some exotic materials, electrons can behave in a very strange way so that they're anions. So they're made of electrons, but because of their strange behavior, we call them anions. All right. So it's anions, not only we have anions, we can control the anions. For example, I can rotate two anions. If the anions can couple to, for example, magnetic fields, then when we control the magnetic field, we can control the anions. We can rotate them. Now, this is a 2D layer. If we add another axis as time, and when we rotate two anions, their world line will look like this. Okay. Now, the idea is to encode information, not in just one anions, but in assembly of anions. So these anions can be very far from each other. If we look at one individual anion, we will not get any information out of this. So the information is only encoded in some assembly of this. So this is a global way to encode information. We can disturb one anion, it doesn't matter, right? So from this, you can already get a test, get a flavor of topology. Now, as I said, I can rotate the anions, therefore I can process this quantum bit. I can rotate and get a different state. But again, the final state will only depend on order and which pair I rotate. It does not depend on the fine details. Therefore, if I somehow disturb this projector, you mess it up. As long as you have the same final state, you still have exactly the same quantum operation. So therefore, this is immune to the noise. And finally, at the end, we can bring two anions together depending on what kind of particles it gives us. We can infer to the final state. So again, we have some global way to store the information. We can rotate them, and this operation only depends on the initial and the final state. It does not depend on the details of how you rotate. And at the end, we can infer, we can bring them together, and based on what they give you, we can infer to the final state. So this is a complete process of computing. Yep. To store the information, to process the information, and to read out the information. This is called topological quantum computation. Well, so you can imagine if it's topological, it does not depend on details, it's immune to the noise, it will keep the coherent state for a long time, will not have that decoherent process problem. All kinds of advantages. But there's one problem with this kind of design. That is, they do not exist. The reason why they do not exist is because these exotic materials that can host these exotic particles, the anions, have not yet been clearly identified. I mentioned this quantum Hall state. Inside the quantum Hall is insulating, on the edge is conducting channel. Now, a direct analogous of this quantum Hall is so-called topological superconductor. Right? So you may be familiar with superconductor. So a superconductor is a perfect conductor. Right? The resistance is zero. Now you may wonder, okay, if you have a topological superconductor, inside the bulk, it's already a perfect conducting state. What kind of edge channel you expect? Turns out, at least for some topological superconductor, the edge state will be a so-called chiral Majorana fermions. And this is that exotic material that we're looking for. And this Majorana fermions, even though it's fermions, it can be utilized to realize that so-called anions. Right? So this is the material that we need to build that topological quantum computer. Let me say a little bit more about this Majorana fermions. So some of you probably know this Dewac equation, right? So Dirac, he combines special relativity with quantum mechanics, and he wrote down a Dirac equation, and he predicts that all the particles have antiparticles. So electron has anti-electron, which is called a positron, and neutron is anti-neutron, proton is anti-proton. But if you look at the equation, so each particle basically is the eigenstate of this equation. Now this eigenstate is a complex number. Now complex number has a real part, has imaginary part. Then another scientist, Majorana, he said, well, what if the solution to this equation is a real number? The real number is a subset of a complex number. The real number does not have imaginary part. If the solution is a real number, the complex conjugate of a real number is itself. So based on this, he predicts that there must be a class of particle that, they're their own antiparticles. Therefore, this kind of particles are called Majorana particles. So far, in the nature, people have not discovered Majorana fermions. But as I mentioned, topological superconductor on the edge, you might have propagating Majorana fermions. Now, in order to control this, the Majorana fermions can also be in the so-called vortex. If you apply the magnetic field in a superconductor, you might have the vortex. And if this is a topological superconductor, the Majorana fermions can be bonded in the vortex, and therefore it's a so-called Majorana fermions as a zero energy Majorana fermions zero mode. Majorana fermions itself is a fermions, but Majorana fermions at a zero energy will be that anyons. Okay, but still, in the past 10, 20 years, people are looking for Majorana zero mode or Majorana chiral Majorana fermions. The one way to look for this is use a so-called heterostructure. So people believe this is very rare in the nature. So they engineer topological superconductors. They use some other topological materials combined with a normal superconductor to make a topological superconductor. But because the challenge of the engineer process, this is very hard for applications. Now, the good news is that roughly 2 years ago, I discovered a intrinsic topological superconductors. So it's not engineered. It's not a heterostructure of another topological material with an ordinary superconductor. It's a bulk material, and this material itself might be topological superconductor. So this, I'll just briefly mention the results. This material is called the uranium ditelluride, and on the left corner, that's how it looks like. You can see, okay, this is enlarged. In reality, this is about a 5 × 5 millimeter size, and at the bottom, this is its crystal structure. Now, how do we know it's topological and it has chiral Majorana fermions? We did a so-called STM. So STM, a superconductor, has a so-called energy gap. Now, STM can measure this energy gap. When our collaborator, when they did the experiment in the bulk of the sample, you can see at the bottom, these curves, when there's a dip, that means there's a superconducting gap, right? So whenever there's a dip, we know, oh, it's a superconductor. Now, when they measure the age, we're talking about the bulk and the age. When they measure the age, now you can see instead of having a dip, a symmetric dip, they find anti-symmetric features, right? There's still, the temperature is still below the superconducting transition, but when they measure the age, they see this anti-symmetric feature. Now, this simply indicates we have something that is moving in one direction and on opposite direction on each edge that gives you this anti-symmetric signal. Therefore, we guess, this is still not a very indirect experiment, but we guess, and it's a logical guess, there's a chiral motion, and it likely is a Majorana fermions. All right. So this is a very rare example of the topological superconductor that hosting the Majorana surface case. So at this point, we have a good candidate. So my friends were saying, the center for the last generation of electronics is called Silicon Valley. If your materials can really be one day be used for topological superconductor, you should create a center called Uranium Valley. We'll see. I'll certainly keep you updated on that. All right. So we talk about how topology can bring a revolution and bring us significant ingredient for our understanding. And we talk about some applications. That's it for my talk. And if you have any questions, welcome to ask. And at the end, I have one advertisement. So, during this COVID time, I stay at home all the time. And, kids keep asking, what kind of thing you do. So I say I work on electron, neutron, proton. And the kids ask, what do they eat? Or where do they play? So altogether, we made up the story. And this is called Quantum Island. the idea is to use a story that kids can understand to teach them quantum mechanics. So this is the first book of the series. In this book, I wanted to introduce them the concepts, and especially that proton and neutron are always together, forming a core, and the electron is outside. So here, the three little kids, and two are very close to each other on their proton and neutron, and that one feels left behind. He wanted to break them apart. So that's the story. And this book is in Amazon. If you Google Quantum Island, Real Friendship, maybe you want to get a copy for your grandkids. All right, thanks a lot. That's all I have. If you have any questions.
So, thank you very much for the great talk. So are there any questions? So you can, I think you can unmute yourself if you want to ask a question, or you can ask by chat. So any questions that anybody wants to ask?
I have a quick question. You can hear me? Can you hear me?
Yes, absolutely, yeah.
Yes.
Okay. Okay, so a qubit can take on an infinite number. Is it true that a qubit can take on an infinite number of different values or states? And did you say they had built the computer with 50 qubits? I mean, how can anything that would be, if that's true about the infinite number of states, can you read an infinite number of states, that sort of thing? I'm just curious about the architecture of that.
Okay, so it's still a two-level system. For example, you have spin up, you have a spin, it can point up or down. In a classical qubit, if one bit, a classical bit, for one bit, it can either be up or down. Now, in order to describe two states, you need a 2-bit, right? You need a 2-bit, one is up, one is down. Even though both have the possibility to be up or down, but at the end, if you want to represent these two states, you need 2 bits, one up, one down. But now if you have a qubit, before you measure, it's a superposition of this up and down. So when you measure it, of course, you read either up or down. But because it's a superposition of up and down, this one qubit can already represent 2 states. So if you ask, so how many states we can have? If we have 50 qubits, the number of states we can get is 2 to 50. All right. So that's the power law, the exponential law.
Okay, so I was wrong about the infinite. There's no infinite going on.
Right.
2 to the 50th power is bad.
Okay, so sorry, go ahead. Sorry.
I have a quick question.
Go ahead.
Sure.
So is there a difference between like a unit of information and an anion? And if so, what is the difference?
Is there a difference between a union of, can you repeat the question again? I didn't quite get it, sorry.
Is there a difference between an anion and a unit of information? And if so, what is it?
If there's so anion and a unit of information. Is that what your question is? Well, okay, it's a good question. Let me think how to answer this. And okay, so when we encode the anions, we do not actually encoding each individual anions. So this is different from for example, you can make a transistor, right? Transistor, a 2-level system. So that transistor itself is what you said, a unit of the information. Is that what you mean? So in this case, we actually we encode in assembly of anyons. So it's assembly of anyons. If you look each individual one, you will not get any information. It's only this assembling of anyons.
So you
answer.
So you put the anyons together and then you can read the information from all of them together?
For example, you have we can have a nanowire. At the end, we can have okay, let's put it this way. The anyons is not the anyons we talk about cannot be isolated. Right? It's not like for example, an electron or when I showed you there's a trapped ion. It's really an isolated two-level system. But this anyons actually is a so-called composite particle. It's not each individual electrons or any individual particles. It's a collective behavior of many, many particles. Collectively, their collective behavior, just like there's anyons. So you cannot isolate any of these anyons.
I have a question.
Uh-huh.
I have a question.
Yes. Yes, please.
I don't know how to. Anyway, my question is the material that was discovered that you showed a photograph of. What is that called again? Is there a way to type that on the screen to see what it's called? Oh,
you mean the material I showed at the end?
Yes.
Okay, it's called uranium ditelluride. So uranium tellurium 2.
Uranium tellurium 2. Okay.
So uranium is at the bottom. Tellurium is next to oxygen and then next.
Got it. Thank you.
Actually, if there was a question, maybe David Coney, maybe you want to ask it yourself or you want me to read it out loud. I'm not sure.
How do you search out materials that are candidates for superconductors? Through math, trial and errors. Okay. Actually, so unfortunately, up to now, we do not have a very good mathematic guidance or a theoretical guidance for, to search for superconductors. We do have some, based on your experience, you do have some intuitions into this. For example, uranium ditelluride is really based on our own intuition. It's not based on any guidance. For topological materials, on the other hand, other topological, for example, topological insulator or other thing, really you can calculate the band structure, and that's how it was discovered. Some theories first proposed, okay, this material is going to be a topological insulator, and someone did an experiment, it turns to be true, but that does not happen in superconductors. So far, there is no theory to tell you, at least for unconventional, we can predict lanthanum hydride to be a superconductor, but that's a conventional.
So thank you, Roger. Do you have anybody else has other questions?
I have one other question. You showed the slide where it showed like almost energy states of way down, and the top one was an integral value was like 1, and the next lower one was somewhat. Do those have anything to do with the energy states of electrons in the material?
Yes. Actually, I didn't mention that. So in a 2D electron gas, remember we talked about the electron moving a field. Actually, that's a very classical picture. But if you think electron as a wave, so in order to make a circle, the wavelength has to be some, it cannot be arbitrary number. It can only be certain numbers. and the wavelength corresponds to certain energy, right? So that also means the electron will have discrete energy state. And that is
that's fine.
level.
Yeah.
So depending on which Landau level you fill, you give that steps.
Okay, that's what I was thinking. Right.
Okay, yeah, that's a very good question. Yeah, thanks.
So other questions?
Oh, sure.
So maybe I can ask a question, Soher.
Okay.
Oh, I thought Sohan wanted. Okay, all right, never mind.
So what's the real evidence for the chi-LH modes that you have in that that compound? I mean, did you perform some sort of Josephson fractional Josephson effect or Shapiro steps or something like that?
So right now, okay, right now is the only evidence. I would say two evidence. One evidence is STM. So on the STM, we saw this, you know, a chiral edge state. Different age, you see different, you see antisymmetric thing. Actually, still not well understood from the theory point of view. But one guess is this is related with Majorana. But one thing is for sure, there's a chiral edge state. That's for sure. Whether this really is related with Majorana is not so clear. Now, another indirect thing, if you have this chiral edge state, that also means you break time reversal symmetry. So we tried so-called Curry effect to see if indeed you have any time reversal symmetry, and we did see time reversal symmetry breaking from the Curry effect. So that is consistent, but of course that
but how hard it is to do a Josephson tunnel? How hard it is to do Josephson?
Josephson, we are collaborating with UIUC. They have been working on this for more than a year. So I would say it's pretty hard since it's been a year and they don't have results yet.
Okay.
Does anybody else have other questions?
Hello, I was going to say that I think some people would already say that there is a uranium valley, and it's called Oak Ridge, Tennessee.
Ah.
Yeah, that's a good point. Yeah.
So, can you hear me?
Actually, I mean, not very clearly.
Can't hear. There's some.
Maybe could you want to type it in the chat, or you can ask, of course, or maybe you can type it in the chat, because the voice somehow is a bit crackled.
Sounded like an alien.
Okay, so yeah, I'm just asking. Oh, sorry. Okay. So yeah, so the question was just asked by chat.
Sorry, that was my computer was messed up. So we're trying to try that again.
I'm not sure. I mean, maybe you'll try it again, but just not sure. I mean, so you're asking about what sort of fermions these are? These Majorana fermions? I mean, so you're asking which sort of fermions Sheng was talking about? Or...
He's the same guy that asked the question about how many anyons you need to encode 1 qubit. So probably it's a follow-up question on that thing.
Okay, how many anyons? 4, let's say.
Depends on the anyons, but the ones you were talking about is 4.
Yeah.
Okay, so does anybody else have any other questions that you want to ask Sheng? Also, if you have problems sort of asking a question, you can ask by chat, of course, as well. Or if you want to ask something else that we misconstrued, you can ask by chat. I guess not. Right? I mean, so I mean, so let's thank Sheng for a great, very nice talk.
Well, thanks for everyone. Yeah.
There is a question about recording.
Oh, sorry. Yes. Yeah, so I'm not sure when it will be available, but it will be available. So it will be available at some stage. I don't know exactly when. It should be probably quite soon. So all these talks, as I said in the beginning, will be recorded. I'll record it. Okay, so if there are no other questions, I mean, let's really thank Sheng. So it was a fantastic job. You set the bar very high for all those that follow you. Okay, so thank you, Sheng.
Okay, all right, have a good weekend, everyone.
Thank you very much. Have a nice weekend.
Thank you.